Ever since the helicopter became a practical operational aircraft, new uses for it have been discovered by every branch of the U.S. Armed Forces. The Army, the Navy, the Air Force, and the Marines all have found that for certain jobs, you just can't beat a helicopter. However, new assignments inevitably mean new demands on power and flexibility. As the helicopter's usefulness has extended itself, we find increasing emphasis on bigger payloads at takeoff, faster climb, higher hovering ceilings, improved control in emergency landings, and higher altitude takeoff capacity. Again and again, helicopter pilots confirmed the fact that an auxiliary power source, which could be cut in during takeoff, landing, and hovering, might double or triple the ship's usefulness if it could be attained without too much overall weight increase. As far back as 1936, a suggestion was made that was someday to furnish the solution, though at that time the problem had not even been broached. It was put forth in an article by the late Jim Wild, American rocket pioneer and one of the founders of Reaction Motors Incorporated. Wild proposed a helical airfoil, more or less like the blades of a helicopter, but powered by rocket engines at the tips and deriving its lift from rotation. Again, in 1945, RMI investigated another application of rocket power to blade tips. At this point, you might say, we were getting warm. But like a lot of good ideas, the blade tip rocket had to wait until a really acute need came along. Such a need arose in the Korean War, when U.S. Marine helicopters found themselves up against the acid test as weapons of rescue and reconnaissance. When a few seconds delay in takeoff or too slow a climb might mean disaster, when reduced payloads meant abandoning wounded buddies to their fate in enemy hands, and when a pilot might have to take off and land in some extremely inconvenient spots. The search for an effective auxiliary power source had acquired a new urgency. The U.S. Navy's Bureau of Aeronautics felt that rocket power was probably the answer, and that RMI had the right background for the job. Quite a few other RMI-developed rocket engines had turned out favorably, including the 3,000-pounder that became the jet assist unit for the Martin PBM flying boat, the 6,000-pound multiple-chamber power plant that became the first engine to push a piloted aircraft beyond the speed of sound. First, the X-1A, holder of the world speed and altitude record for piloted craft. Then the Skyrocket, now in use by the NACA to study supersonic flight. An 8,000-pound thrust engine with a unique independent swiveling action to provide guidance for a high-altitude missile. The big alcohol and oxygen engine that furnished 10 tons of thrust for the Viking, which holds the world's altitude record for single-stage rockets. And some others of far greater power, still hidden behind the barriers of military security. So work was started on Project ROR, meaning Rocket on Rotor. Needless to say, when you have to reorient your thinking from rocket engines, the size of the Viking, to one hardly bigger than a salt cellar, which nevertheless has to carry a solid punch, you can expect to run up against certain problems. But after a few false starts, a basic idea was evolved that seemed reasonably sure to work. The design was simplicity itself. A tank of hydrogen peroxide is mounted on the rotor. Centrifugal force feeds the propellant out radially through the rotor blades to the rocket engines mounted almost invisibly at the tips. A catalytic unit inside each engine decomposes the peroxide, generating live steam. Thrust is created by the reaction from the escaping steam and hot gases. There's no flame, nothing to be seen, and very little added noise. Plans called for the rocket engines themselves to weigh less than 2 pounds, with an overall dry weight for the entire system of not more than 75 pounds. If we could hit that target without too many other unforeseen headaches, Project ROR would be in business. Right from scratch, Project ROR was a cooperative one. between RMI and the Sikorsky helicopter people with the sponsorship and guidance of the Navy's Bureau of Aeronautics. In the preliminary design stage, the Sikorsky HRS-2 was selected for the experiment. A simple modification of the existing blade permitted installation of the ROR engine and fuel feed line. The blade tip was transformed into a detachable fairing. Preliminary feasibility tests were carried out on Sikorsky's World Test Stand. They proved that the basic design was definitely a workable one, though certain bugs, of course, remained to be ironed out. The road to every worthwhile design is strewn with discarded errors, and Project ROR was no exception. Here's one of them, which came to be known as Myrtle, the mysterious manifold. The idea of that manifold running around the outside was to equalize the fuel pressure and secure uniform feed. However, the effect was exactly the opposite. One of the feed lines would almost invariably be starved for fuel, while the other two would be, so to speak, overfed. Then there were the electrically operated fuel valves. All three were independently actuated. Too independently, as it turned out. They acted something like an orchestra with no conductor. This was another noble experiment. You and I know that a liquid can't flow uphill. Well, this did. It all had to do with the bleed tubes running to the top of the tank. Even when they were relocated considerably past the liquid level inside the tank, they went on merrily spouting fluid whenever the rotor got spinning at full speed. The first catalytic units were built up out of individual discs, one at a time. But this seemed like quite a lot of trouble. So, lovers of efficiency usually tried to save some time. But all they got was more trouble. Eventually, a more rational arrangement suggested itself. And one by one, the other gremlins got smoked out too. We got rid of Myrtle, found we got better pressure equalization without any manifold at all. That liquid is still running uphill, but we cured the practical difficulty by sticking a few baffles in the vent. We replaced the three rugged individualist electrically operated valves with one electrical rotary actuator mechanically linked to all three valves, which gave us positive simultaneous opening and closing with no ifs or buts. In static test runs, every possible pressure condition the engine might have to undergo in actual flight was simulated. Needless to say, at every step of the testing process, new testing equipment had to be invented right on the job. This rig was designed and developed in order to simulate as nearly as possible the kind of vibration conditions the tank would be exposed to during flight. It permits the tank to be rotated at any desired speed within the normal operating range. It also provides simultaneous vibration in both the horizontal and vertical planes with resultant loads that considerably exceed the operational conditions of the Sikorsky helicopter. Intermittent shock loads can be fed in to simulate the vertical gust loading which the aircraft encounters in flight. This rig proved extremely useful in determining distribution of the propellant through the feed system. Later on, this same rig was used for qualification of the final tank design, during which 40 hours of this rugged treatment were put on a tank to meet Navy's safety specifications. But we're getting a little ahead of our story. The preliminaries over, preparations were begun for testing on an actual helicopter. The Marine Corps flew in a stock HRS-2. It got tied down on a concrete test pad specially designed by Sikorsky and built at RMI by Navy personnel. To get the ship ready for ROR, a few standard helicopter parts are first removed, and the extension shaft is installed with a simple set of lock rings. Then the tank goes on, secured with a lock nut. Finally, the standard lifting eye is replaced, this time on top of the tank assembly. The rocket engines are secured to the blades by two standard bolts on a modified end plate. To equalize any discrepancies in balance between the blades, balance weights are mounted over each engine as required, held on by a straddle block assembly. When all that has been straightened out, the detachable fairing is put on, leaving only the tip of the engine showing. The feed lines are supported in the spar cavity by rubber grommets to protect them against vibration stress and possible buckling. The tank is connected up with the blade lines by flexible tubing and standard AN connectors. The electrical elements of the ROR system comprise the firing switch, rotary actuator, arming indicator light, and a timer to show how much fuel is left in minutes of remaining operation. They are connected into the airplane's regular 24-volt DC power circuit. The valve actuator is mounted to the underside of the tank. Contact with it is made through slip rings that lock onto the hub just above the main rotor head. The actual installation of parts can be made in less than a day. With the system installed, the ROR was ready for its first test on an actual helicopter under the eyes of Navy officials. The first test run is made with water instead of fuel. Results indicate that fuel distribution will be satisfactory. Next stage, the first live run with live fuel. If the ROR system performs according to plan, it should add approximately 35 pounds of thrust per blade at rated RPM. This time, the gauges will also measure actual blade lag angle, which is, of course, a function of thrust. As the main engine comes up to full speed, the pilot presses the ROR firing switch and energizes the circuit. This first test run with live propellant is definitely satisfactory. Added thrust per blade figures out to more than 35 pounds. This service truck was also developed by RMI on a basic chassis provided for us by the Navy. It carries 600 pounds of hydrogen peroxide, enough to service 2 ROR units. A heater for cold weather operation, a hoist for lifting the peroxide drums, a nitrogen cascade pressure system, and water for flushing any accidental fuel spillage. With the right equipment, plus a few minutes common sense instructions, anyone can learn to handle hydrogen peroxide just as safely as aviation gasoline or any other high-energy fuel. The ROR had had a good beginning, but many questions still remained to be answered. How would it work out in actual flight under varied conditions of load, temperature, and weather? What sort of maintenance problems would develop over an extended period? What would be the life of the system? Could uniformity of performance be maintained in unit after unit on a production basis? How would ROR affect the helicopter's aerodynamic balance? What would happen if one or even two of its 3 engines failed during flight? Down at the Lakehurst and Patuxent Naval Air Stations and at the Marine Corps Air Station at Quantico, the real grind began of qualification testing in actual flight. Hovering at various altitudes, climbing, descending in auto-rotation to simulate engine-off emergency landings, with normal and abnormal payloads, with only 2 rocket engines functioning, timing, measuring. 6 months and several hundreds of tests later, Project ROR was ready for demonstration and performance before top Navy, Marine, Army, and Air Force officials. The meeting took place at Anacostia Naval Air Station September 16, 1954. The Marine Corps had provided 2 HRS-2 Sikorsky helicopters, one with ROR and one without. Both were loaded with a maximum payload for sea-level takeoffs. Both craft were lined up on the runway. They're off. Now watch the added lift provided by the rocket power. The one with ROR is climbing more than twice as fast as the conventional ship. A few minutes later, ROR demonstrated its ability to add several thousands of feet to the hovering ceiling of the HRS-2. After refueling, the ships are ready for the final demonstration. Extra takeoff payload. The stock HRS-2 will carry its regular deadweight payload, the equivalent of 6 troops and 2 pilots. The ROR-equipped craft will attempt to take off with an added payload of 800 pounds, equivalent to at least 4 extra Marines in full combat equipment, or 12 men in all. Project ROR has now undergone all design and qualification testing and has successfully passed its demonstration and performance tests as well. Naturally, improvements can still be made, particularly in servicing and maintenance. But, just for the record, here's a recap on the specifications and the performance figures as of January 1955. Total dry weight of a ROR system as installed in the HRS-2 is 67 pounds. The crucial element, the driving engine, weighs only 1 pound. The fuel tank is an aerodynamically clean, modified hemisphere. It holds 300 pounds of propellant, or enough for at least 6 minutes continuous operation at full power. In practice, that's enough for about 12 normal takeoffs. Fuel pressure is provided by the centrifugal force of the rotor's motion. A regular single-throw toggle switch in the cockpit is used to energize an electric rotary actuator mounted on the tank, which actuates a mechanical linkage that opens all 3 fuel valves simultaneously. Return springs close the valves whenever the pilot's switch is returned to off. Decomposition of the hydrogen peroxide propellant is achieved by passing it over a catalyst contained in a replaceable cartridge which fits into the inboard end of each rocket engine. The exhaust, consisting of live steam at about 1300 degrees Fahrenheit, is invisible, except for an occasional starting puff. The rockets do not add substantially to the noise of the main engine running at full power. The increase in power with ROR is more than 20% over that supplied by the main engine of the HRS-2. ROR has demonstrated an increase in takeoff payload at sea level of 100%, while the dry weight increase is less than 1%. With ROR, the hovering ceiling of the HRS-2 is increased by many thousands of feet. The actual figures are still classified. With ROR, the rate of climb is doubled at all operational altitudes. In auto-rotation, ROR cuts the rate of descent to less than half. Or, to put it the other way, the gliding distance is more than doubled. This is the difference in possible landing area from the pilot's point of view. Over 4 times as much choice. And, of course, ROR gives him much better control over the ship during auto-rotation. To get the equivalent improvements from the main power plant would require an estimated increase in dry weight of at least 200 pounds, not to mention the structural changes that might be needed to accommodate the heavier main engine and transmit safely its increased power to the rotor system. But with this light, safe, and practical auxiliary power source now available, future helicopters can actually be designed around a smaller main power plant with all the resultant advantages of bigger payload per pound of aircraft, lower overall cost, better performance under critical conditions, and greatly increased potential tactical life of any given design. With ROR, the performance of most existing types of operational helicopter can be greatly improved. And there is no longer any room for doubt that in the history of rotary wing aircraft, something definitely new has been added. Ever since the helicopter became a practical operational aircraft, new uses for it have been discovered by every branch of the U.S. Armed Forces. The Army, the Navy, the Air Force, and the Marines all have found that for certain jobs, you just can't beat a helicopter. However, new assignments inevitably mean new demands on power and flexibility. As the helicopter's usefulness has extended itself, we find increasing emphasis on bigger payloads at takeoff, faster climb, higher hovering ceilings, improved control in emergency landings, and higher altitude takeoff capacity. Again and again, helicopter pilots confirmed the fact that an auxiliary power source, which could be cut in during takeoff, landing, and hovering, might do a lot of good ideas. The blade tip rocket had to wait until a really acute need came along. Such a need arose in the Korean War, when U.S. Marine helicopters found themselves up against the acid test as weapons of rescue and reconnaissance. When a few seconds delay in takeoff or too slow a climb might mean disaster, when reduced payloads meant abandoning wounded buddies to their fate in enemy hands, and when a pilot might have to take off and land in some extremely inconvenient spots. The search for an effective auxiliary power source had acquired a new urgency. The U.S. Navy's Bureau of Aeronautics felt that rocket power was probably the answer, and that RMI had the right background for or triple the ship's usefulness if it could be attained without too much overall weight increase. As far back as 1936, a suggestion was made that was someday to furnish the solution, though at that time the problem had not even been broached. It was put forth in an article by the late Jim Wild, American rocket pioneer and one of the founders of Reaction Motors Incorporated. Wild proposed a helical airfoil, more or less like the blades of a helicopter, but powered by rocket engines at the tips and deriving its lift from rotation. Again, in 1945, RMI investigated another application of rocket power to blade tips. At this point, you might say, we were getting warm. But like a lot of the job. Quite a few other RMI-developed rocket engines had turned out favorably, including the 3,000-pounder that became the jet assist unit for the Martin PBM flying boat, the 6,000-pound multiple-chamber power plant that became the first engine to push a piloted aircraft beyond the speed of sound. First, the X-1A, holder of the world speed and altitude record for piloted craft. Then the Skyrocket, now in use by the NACA to study supersonic flight. An 8,000-pound thrust engine with a unique independent swiveling action to provide guidance for a high-altitude missile. the big alcohol and oxygen engine that furnished 10 tons of thrust for